So, well, we start a new chapter of the book with this section. This chapter is Understanding Functions via Polynomials and Power Series. The point of this chapter is that even functions that we think we know, like sine of x, e to the x, natural log of x, inverse tangent of x, you think that you know what those functions are, but if you know what a function is, shouldn't you be able to tell someone what the value of the function is when you stick in an x-coordinate in the domain, or at least tell them what the value is to some desired level of accuracy? And yet, for those functions, we have trouble calculating by hand, like what's the sine of 1? Another way of looking at this question of that problem of not understanding a function is, does your calculator understand functions better than you do? So your calculator can tell you what the sine of 1 is to the accuracy of your display. What the hell is it doing when it does that? We'd like to look at that. But beyond what your calculator can handle, there are other things that we'd like to know in order to understand functions better. If we understand functions well, we ought to be able to see that this complicated expression in terms of these functions equals this expression in terms of these functions, so that you have these identities, or that this function is approximately equal to this function over a whole range of values of x, not just give me the value of the function at this one point to this accuracy. So these are the types of questions that approximating functions by polynomials and writing functions as power series can address. The first section in this chapter is going to start out fairly simple. We're actually going to approximate polynomials themselves, not approximate other functions with polynomials, but talk about the issue of how you approximate a polynomial well by pieces of the polynomial. So you know what a polynomial is. We've talked about it before, and you almost certainly learned it in high school. Actually, there's a polynomial I want to pick on as an example throughout today, just to agree with what's in the book. So a typical polynomial looks like, well, here's a typical polynomial. I want to say that technically there's a difference between a polynomial and a polynomial function. This context will always make this clear. I don't think there'll be any confusion. But technically, the polynomial is the algebraic expression and is more, it's just the formal way that it's written. It's constants times powers of x, or in a few minutes we'll have powers of x minus a constant. The function that it gives you, the function that it defines when you plug in various powers of x, technically is a different object, a different thing, but the distinction will not be, there will be times when it's important, but it'll always be clear from context which way we're thinking of it. So this is a typical polynomial. This polynomial has degree 5. Right? This is the degree is the highest power of the variable that you see with a non-zero coefficient. More generally, using our summation notation that we used, well, we've used it several times, but we used it last when we talked about Riemann sums. You take the sum as k, it doesn't matter what you call this index, as k goes from 0 to d of some constants times powers of x. So this means we're writing C0. I should say that even though 0 to the 0 is an undefined quantity, when you're dealing with polynomials and power series, when k is 0, we like to write this nice expression. When k is 0 by x to the 0, we always mean 1, even if x might be 0. So we are adopting the convention that is standard in this, that x to the 0 equals 1 even when x is 0. I'll say it again, I'm not saying that in all problems, in all circumstances, you want to define 0 to the 0 to mean 1. Just when we're in this chapter, when you see the expression x to the 0, it means 1, even in the case where x might be 0 itself. So then you get, so the sigma means add. So you let k be 0, and you get this. Then you add what you get when k is 1, which is a c1 x to the 1, but that's x. Then you add to that what you get when k is 2, plus a c2 x squared, and so on. You keep adding until you get to c sub d x to the d. I'm thinking of d as the degree, but d would only be the degree if, in fact, so it's the highest power term, but you need for it to appear with a non-zero coefficient. So I wrote d thinking degree, but you really need, if c sub d is unequal to 0, then the degree, so I'll write deg, the degree of p of x here is that d, the highest power term that appears with a non-zero coefficient. All right. We want to look at some parts of the polynomial. We're going to define, so let me come back to our example over here. If we start with this polynomial, I'll write this in the summation notation, so the sigma notation in a minute, but let me give an example first. So if we start with this polynomial, p of x equals 4 minus 2x plus 5x squared plus 9x to the 5th, 9x to the 5. If you start with this, we're going to see that for a lot of our problems, the things we want to talk about, that it will be useful for us to look at pieces of this sum, the pieces that start at the degree 0 term, and then you include more and more pieces. So we'll have a part that only goes out to the degree 0 term. That's why I'm writing a 0 there. And I just mean, oh, just take all the terms added together up to the degree 0 term. Well, that's just 4. P1 sub 1 of x. I mean, take all of the terms in this sum, or sums and differences, up to the degree 1 part. So you'd get 4 minus 2x. For P2, P sub 2, take all the terms up to the degree 2 term, and so on, except, I say and so on, but you may have noticed there is no x cubed term. So what do I mean by P sub 3 of x? Well, you should think it's 0x cubed, and now you include that, but that means it'll look just like this. So yes, you include the cubed term, but that's 0, so including it doesn't change anything. So P2 and P3 are the same. P sub 4 of x, you would go out to the degree 4 term, but there is no degree 4 term. The x to the 4th term has a 0 in front of it. So again, P sub 4 of x is also the same as P sub 3 and P sub 2. And then P sub 5 of x would be the whole polynomial because we've gone out to the degree. So it'll just be 4 minus 2x minus, plus 5x squared plus 9x to the 5. All right. We call these are partial sums. Partial sums of p of x. And we can't say degree. What we'd like to say is this is the second degree partial sum, and this is the degree 1 partial sum, and the degree 0 partial sum, except p sub 3 isn't a degree 3 polynomial, because the degree 3 term is, or the order, the x cubed term is 0, has a 0 for a coefficient, and this also isn't a 4th degree polynomial. This is a 5th degree. So we don't want to say degree, so we use another term. We would say, for instance, this is the 4th order. The 4th order partial sum of p of x. So yeah, the 4, you should think of it as kind of the degree, except we left, those x to the fourth term has a 0 in front of it. The x cubed term has a 0 in front of it. Also notice we could talk about the sixth order partial sum and the seventh order partial sum. Well, they'd all be the same as p of x because all the other powers of x have zeros in front of have 0 coefficients. And so if you write the sixth order partial sum, which would mean you include the power of the sixth power of x, well, you won't see it because it has degree 0. All right, that's just some terminology. In our sigma notation, what it means is that if you've got some p of x already, then what we mean by p sub n of x is you just go out to the x to the n term. So that just means we put an n here. But you have the same coefficients as you had in the polynomial p of x. So ck x to the k. So it looks the same. That just changes to an n. It just means you stop adding when your power of x gets up to n. All right. Why would we look at the partial sums? Because there's kind of an obvious principle here, but it actually gives us stuff, and you may never have thought about it before. So let me come back to this example. Here's an example of a polynomial of degree 5. Typically, you think of this term, the 9x to the fifth, the highest term with a non-zero coefficient, you think of that as the most important term in the polynomial. When x is big, this term is so much bigger than those, they practically don't matter. You know, that it's the 9x to the fifth that's big. It's so big, it overwhelms all the other terms. Or if x is very negative and big in absolute value, so negative 300 trillion, this term is so much bigger than those, they're essentially insignificant. And so you have this tendency to think of the high powers of x as being more important. But that's true when the absolute value of x is big. What if the absolute value of x is close to 0? And this is the fundamental observation that when x is close to 0, so it could be positive or negative. So really you could write the absolute value of x is close to 0, but that's the same as saying x is close to 0. What's true is that when x is close to 0, I think 0.001, when you raise something that's smaller than 1, or has absolute value smaller than 1 even, when you raise that, or not even, has absolute value smaller than 1, when you raise that thing to a higher power, its absolute value gets smaller. And so when x, think if x is 0.1, x squared is 0.001. Right? It's closer to 0. When x is close to 0, lower powers of x are, I'm going to write this, it's not a, put it in quotes, are more important. The higher powers of x are closer to 0. So what does this mean? It means if you know that x is close to 0 and you want to approximate this polynomial, leaving off high-powered terms should give you a reasonable approximation. So maybe high, where high power means as high as you feel like. I mean, it's an ill-defined term, but for instance, if when x is close to 0, if we leave off the 9x to the fifth, so take, well, what's the second, third, fourth, or fifth order partial sum? Sorry, not the fifth. Take the second, third, or fourth order partial sum. we should get a good approximation to the entire p of x. Or maybe even if we leave off all the terms of degree 2 and higher. So if we just take the first partial sum, that should give us a reasonable approximation if x is close to 0. Let's plug in some numbers and see. But the point is, and maybe I'm beating this into the ground too much, and maybe it's just so simple I hardly need to say anything, that if x is close to 0, when you raise x to higher powers, you get even closer to 0. So those higher powers don't matter much. So I'll rewrite p of x again. P of x is 4 minus 2x plus 5x squared plus 9x to the fifth. So let's plug in some numbers and something that's easy to raise to powers. So I'll suppose x equals a tenth. So 0.1. Right? Let's approximate p of x by, well, let's approximate it by just its 0th order partial sum. That's a constant approximation. That's not too exciting. By p of x, p1 of x, and p2 of x. And see what we get. All right, so when you're approximating p of x by p0 of x, this means we're saying, so p0 of x, we're saying, oh, this is approximately, where approximately, of course, is an ill-defined term. We're saying, let me put p over there, is approximately p0 of x. It means we're saying that when x is close to 0, p of x is approximately equal to 4, well, just 4, the 0th order partial sum. So you just go up to the x to the 0 term. All right, p of x is approximately 4 if you use this approximation. How bad is that approximation when x is 1/10? Well, we have to know what p of a tenth is. So let's go ahead and record that. In fact, this isn't bad to calculate because once we make it a tenth, we're kind of using decimals. So we are using decimals. P of 1/10 is 4 minus 2 times 0.1 plus 5 times 0.1 squared plus 9 times 0.1 to the 5th power. Well, you might get out a calculator, but you shouldn't need to. This is 4 minus, this is 0.2, plus, this is 0.00, when you square a tenth, you get 100th, 0.001, sorry, 0.01, not 0.00, let's not get carried away, 0.01, and then plus 9 times, and then 0.1 to the 5th, you get 0.00001. Okay, so, 1, 2, 3, 4, yes, okay. And so this is 4 minus 0.2, 3.8, and then plus 0.05 plus 0.0009. And so we get 3.8509. I think I lost a 0. Did I? No. Yes, I did lose a 0. Sorry. 0.009. 1, 2, 3, 4. Yes. Okay. So we get 3.85009. Right. Okay. So how close? So that's the real p of 0, 1. I won't write it, but how close is this to that? Fairly close, but we'd like to do better. approximating a function as being constant is boring, and it's not very accurate, but it's not too bad if x is close enough to 0. How close is close enough? It depends on what you're doing. So let's try. All right. What if we approximate p of x? We say, oh, it's approximately equal to the first order partial sum, which is 4 minus 2x. So now we're saying that, yeah, when x is close to 0, higher order terms like the x squared and the x to the fifth term don't matter as much, and this would be a reasonable approximation. Well, how reasonable is reasonable? Again, when x is a tenth, we know this side. We just figured it out. It's 3.85009. This side, you just take 4 minus 0.2. So this side is 3.8. How good is that approximation? Well, you know, it's within 0.05009. Again, good for a lot of purposes, not as good for other purposes. What if we use p of x as approximately p sub 2 of x, so the second order partial sum, which is the same as the third and fourth order partial sum. So this is 4 minus 2x plus 5x squared. Well then, this side, when x is 1/10, remains 3.85009. And we're saying that's approximately the 3.85. This side is the 3.85. Well, now we're really close. This is within 0.009. So yes, you get a very good approximation using p sub 2 of x. As x gets closer to 0, all of these approximations get better, because if we made x, well, something closer to 0, all these higher power terms become even more insignificant. Like we could, to do it by hand, we could make this 1/100th. And then you'd see all of these approximations improve. Well, you wouldn't see, I guess, sorry, you wouldn't see, yeah, you would. I was going to say you wouldn't see this one improve, but yes, the original one where it's constant, but yes, you would. So this is very basic, and yet people have trouble with it. That yes, when x is close to 0, and you have a polynomial written in powers of x, that it's the lowest degree terms that are most significant. The higher order terms, the higher powers of x, matter less. Another standard question, not just approximate this at different values. Another standard question, I don't want to erase this. Another standard type of question would be, something like, so here's an example. When x is close to 0, I'm referring to this p of x. So p of x minus 4 plus 2x divided by 5 is best approximated by what power of x? Okay, so the p of x here refers to this p of x. So when x is close to 0, this expression, p of x minus 4 plus 2x divided by 5, so this function, is best approximated by what power of x? Well, I didn't just pull this out of nowhere. What is p of x minus 4 plus 2x? Well, that's where I've put these two terms over on the other side. So this p of x minus 4 plus 2x, well, that's what I get when I move these terms over there. This equals 5x squared plus 9x to the 5th power. So if I take 1/5 of this, then I'm taking 1/5 of this side. So I multiply this side by 1/5. That divides that away, and I get this. So this expression right here, this function, this equals x squared plus 9x to the 5 over 5 and so the question is, when x is close to 0, x squared plus 9x to the 5 over 5 is best approximated by what power of x? Well, when x is close to 0, lower powers of x matter more. So if you're just trying to approximate this by a single power of x, you would use the x squared term. The x to the 5th term, the x to the 5 term is small, is very small, insignificantly small when x is close enough to 0. So the answer, 2. Which power? 2, or the second power. So 2, or the x, by the function x squared, because you just take this first, well, partial sum, but it's really the second order partial sum. You take the first non-zero term. So yeah, that one. All right, maybe I've gone on too long about this, that it's blatantly obvious that when x is close to 0, higher powers of x matter less. But one of the things we care about, or an important thing that we care about, is not just approximating functions, and in particular polynomials, well near x equals 0. What if we wanted to approximate a polynomial very well near x equals 1, or near x equals 2, or the square root of e? Or what if we want to approximate a polynomial near some other fixed x value? So we need to talk about polynomials that are written in different ways. So that's why I even mentioned there's a difference between a polynomial and a polynomial function. We're about to write polynomials in a different way. The polynomial functions that we get are the same as the polynomial functions we get from powers of x. But now we're going to take powers of x minus some fixed constant. So that gives you a different polynomial, but not a different polynomial function. I'll say it again. The context should make it clear, and you shouldn't ever be confused by this distinction. So a polynomial centered at x equals a, or actually let me just say centered at a, where we're thinking of a as a fixed x value. Centered at a is a polynomial of the form so maybe I'll use a q. I mean, I could call it p again, but since I was using p's for polynomials centered at x, maybe a q would be nice. K equals 0 to d, I'll still use that. Some constant, maybe I'll use b's here, not that it matters b, but instead of having powers of just x, you have powers of the quantity x minus a raised to the k. So again, I'm thinking of d as the degree, but it would only be the degree if d is not 0. So actually, let me write out what this looks like. When k is 0, we get b0, x minus a to the 0. Again, just like x to the 0, we're going to say that's 1. X minus a to the 0, we're going to say that's 1. So you just get b0 plus what you get when k is 1. So you just have powers of x minus a, where before we had powers of just x. So in this setting, our normal polynomials, which are just powers of x, are centered at 0. That's our favorite place to center things, at 0. So something of this form. So as an example, we might have q of x equals, just pick something, 3 minus 5 times x minus 1 plus 7 times x minus 1 cubed. Here, that's a polynomial, but centered at x equals 1. Of course, we could expand this. We could expand this and rewrite it as centered at 0. You could, that's a different way of writing it, so it's a different polynomial, but it would be the same function. All right, but I'm just going to say polynomial centered someplace, and it should be clear that, I'm thinking of it, polynomial centered at 1. So this is centered at 1. And a lot of people would say centered at x equals 1, but that starts to confuse people, because if you put in x as 1, you just get the number 3. What are you talking about? So this is centered at 1. All right. What's so nice about polynomials centered at different places? Well, what's true now is that just like powers of x, when x is close to 0, higher powers matter less. Higher powers of x minus 1 matter less when x minus 1 is close to 0. But that means x is close to 1. So the whole point of centering, of writing your polynomial is centered someplace else, is that when you have a polynomial centered at a, that higher powers, when x is close to a now, so that means x minus a is close to 0. The higher powers of things that are close to 0 matter less. So when x is close to a, the lower powers of x minus a are the important ones. So the most significant. So again, we define the partial sums where you only go out and take the first however many terms in this summation that defines the polynomial, like the second partial sum, we would go out to the power of 2. And you now approximate, if you want to approximate a polynomial that's centered at some other value, so we'll use this one, that's centered at x equals 1, then, yeah, if you want to approximate it well for x near 1, you just use however many smaller, lower degree terms as you want to get the desired accuracy. So let's take that one. So suppose we take this q of x. So when we want to approximate it when x is close to 1 now, not 0. So when x equals 1.01, so that's close to 1. When x equals 1.01, how close is q of x to, let's take q sub 1 of x. So the first order partial sum, so we go up to the power of x minus 1 to the 1. So this just means we go up to the power of x minus a to the 1. So 3 minus 5 times x minus 1. So there's our question. Well, we'll just check. First of all, what's q of 1.01? Q of 1.01 is 3 minus, notice that you wouldn't want to multiply this out and then plug in 1.01, even if you could, or even if you had it sitting in front of you. You'd still want to plug 1.01 into this, because then you subtract the ones and you see the small powers that you get. So you get 3 minus 5 times, and I'll write it out this one time, but you get 1.01 minus 1 plus 7 times. Plus 7 times 1.01 minus 1 cubed. So what is this? This is 3 minus 5 times, well, you subtract the 1, you get 0.01 plus 7 times 0.01 cubed. So this is 3 minus 0.05 plus 7 times, all right, this is 10 to the negative 2 power. So we get 10 to the negative 6th when we do that. So 0.0000001. 1, 2, 3, 4, 5. Yes, that looks good. And so we get 2. When you do this, you get 2.95. 2.95, but then you add 0.0007. 2.950007. Yes. Okay, so that's what we get for Q itself at 1.01. What happens when we approximate it just by this first order partial sum? Well, that would have been just this part. This part is P sub 1, Q sub 1, sorry. Q sub 1 of 1.01. Right, we just do this part. So it's the 2.95. How close is 2.95 to 2.950007? Well, it's to within 0.000007. Yes, it's extremely close because we took an x that was close enough to 1 that happened. And you can see where, yeah, once things are written in terms of powers of x minus 1, and then you take an x that's very close to 1, of course, you see that higher power terms are less significant. So this is the reason why we will, throughout this chapter, center polynomials at places other than 0, although centering at 0 is kind of our favorite thing to do. We will see later that we'll do this not just for polynomials. We'll do this for polynomials that never end. So those are called power series. And we actually looked at those when we defined e to the x. We defined it as an infinite sum of powers of x times coefficients. And that's where we're headed with power series. And the point is that when x is close to the center, even if you just keep going all the way out to infinity, that if the coefficients are doing the right thing, then the terms get so small that even though you're adding an infinite number of them later, it doesn't change the value significantly. And so you just get a good approximation by taking the fairly small partial sums by only going out to some fixed power of x, or x minus a. All right, this leaves us, we're left with a very important question. And that question is, all right, suppose, okay, we now know if you've got a polynomial written in powers of x, and if x is close to 0, you can approximate the polynomial fairly well by taking one of the low partial sums, one of the low order partial sums. Just go out, take the first few powers of x starting at 0 and go up to, just take a few. We also know that if you've got the polynomial given to you in powers of x minus a, then it's easy to use, then you can use the first few terms of that to approximate the polynomial when x is close to a. But what if you're given a polynomial in powers of x, or something else, and you want to approximate it near x equals something other than 0? So For instance, suppose we had this polynomial right here. So written in powers of x. But what we want to do is approximate p of x by, let's say, a third degree polynomial. So I'm not saying order, I really want third degree, although it's possible that when we do this, you don't know what we're about to do, but when we calculate the coefficient in front of the cube term, we will get a 0, but we'll see. Approximate p of x by a third degree polynomial when, well, we'll keep picking on 1, when x is close to 1. All right, this is what we'd like to do. Now, we know how to approximate polynomials when x is close to 1 if we were given the polynomial in powers of x minus 1. But we're given this polynomial in powers of x. So what we would like to do is, given a polynomial in powers of x, we would like to know how you can rewrite the polynomial centered someplace else. And once we do that, then we do this just by picking up, we go out through the x cubed term in the partial sum once this is written in powers of x minus 1, assuming that the x cubed the x minus 1 cubed term doesn't have a 0 coefficient. All right. So our question now is, I'm given a polynomial, p of x, and now I just need to assume it's a polynomial function. It's kind of irrelevant how it's written. So here's what we need to do right now. Given a polynomial function, p of x, so given a polynomial, p of x, how do you rewrite p of x so that it equals, so rewrite p of x as q of x equals, the sum as k goes from 0 to d of bk x minus a to the k. So you start out with some polynomial function. I mean, you could picture it having powers of x, but it's irrelevant. So I could have written function here, but it doesn't matter. How do you rewrite p of x so that it's centered at a? So the whole question is, what are these coefficients? bk. So we've got this 4 minus 2x plus 5x squared plus 9x to the 5. And what we want to know is, what do the b's have to be so that this equals b naught, so b sub 1 times x minus, well, for our question, the a was 1. But let me just, well, yeah, I'll put an a as 1. Plus b2 times x minus 1 squared plus b sub 3 times x minus 1 cubed plus b sub 4 times x minus 1 to the 4th plus b sub 5 times x minus 1 to the 5. We want to figure out what these b's have to be to make this side equal this side as functions. What should be clear is that you go out to the same power as the degree over here. The highest non-zero, the degree over here is 5. You need degree 5 over here, and the only place you'll get it is from this highest power term. So yes, you can immediately conclude that, oh yes, the degree of this written polynomial centered at a has to be the same as the degree of this for them to be equal. But how do you figure out what the b's are? These coefficients over here on the right. Well, one thing you could do is kind of an inductive algebra problem. You know that the coefficient in front of x to the 5 over here has to be the one in front of x to the 5 here. But the coefficient in front of x to the 5 is b5. So we'll need a 9 here for b5, so that when we expand this, you would get 9 times x to the 5. But then you get all those terms you get from expanding. They'd be multiplied by 9. You would subtract them from both sides of this equation and then say that, aha, whatever remaining x to the 4 terms there are, that's what the coefficient in front of x to the 4 over there needs to be b4. And then you could expand and subtract, and once again, you could do this. It works. It's time consuming, and we'd rather not do it. It's slow. It takes a lot of writing. And so what else could we do? And the answer is really simple. And let me not do it with this specific example because I don't want to disguise what's happening. I think it would be more clear what's happening. I'm going to erase my question. But I think it will be more clear what's happening if I do this just written out like this. So suppose I want p of x to equal some b0 plus b1 times, and I'm going to assume I'm centered at an arbitrary a, plus b2 times x minus a squared plus b3 times x minus a cubed, and then I'm going to put some dots, plus b sub d times x minus a to the d. We can find b's that make this work. As I said, you could do the algebraic calculation that I was outlining a minute ago. But this is a calculus class. Maybe some calculus would help us. And it does. So this is our q of x over here. So this is q of x. And the big deal, p of x equals q of x. So these are both polynomials. So these are polynomials. If and only if all of their derivatives, right? Polynomials are differentiable any number of times. So all of their derivatives are the same. Where at any x value you want, all of their derivatives are the same at any fixed x value. And in fact, you don't need all of their derivatives for them to be equal. We know their degrees have to be equal, so that you could just say all of their derivatives up to the degree of the polynomials are the same at any fixed x value. But there's one fixed x value that's particularly nice on the right, and that's when x is a, because when x is a, all these higher powers of x minus a are 0, and if you keep taking derivatives and plugging in x equals a, it will tell you what the b's have to be in terms of the derivatives of p evaluated at a. So let me run through that. So we want, for instance, we want to find the b's that work over here. You just start taking derivatives. So, well, actually, not at first. First, you plug in x equals 1. For these to be equal at x equals 1, over here, let me just call this p of x. Over here, we get p of 1. Right? So when I plug in x equals 1 here, I just get p of 1. When I plug in x equals 1 over here, this is 0, 0, 0, 0, 0. All I get is b0. So b sub 0 has to be p at 1. Great. So you just plug in 1 for x, and you get whatever you find, and that has to be b sub 0. Okay. What about when you take derivatives? Well, over here, I'm just going to write, so this was p of x. I can take derivatives of both sides, and what I should get is p prime of x, or what I do get, p prime of x equals, what's the derivative of this side? Well, the constant term goes away. plus a b1 times, take the derivative of x minus 1, that's just 1, plus, and then you get a 2b2 times x minus 1, plus a 3b3 times x minus 1 squared, plus a 4b4 times x minus 1 cubed, plus a 5b5 times x minus 1 to the fourth. Each time I was using the power rule to take the derivative of this and the chain rule, but the chain rule in an easy form, the derivative, for instance, of x minus 1 to the 4, by the power rule you bring the 4 down, put a 3 there. By the chain rule you have to multiply times the derivative of x minus 1, but that's just 1. And so you get this. And now again you plug in x is 1. You plug in the center of this polynomial over here. And when you plug in x is 1, you get p prime of 1 equals, well now all of these terms are 0 when x is 1. 0, 0, 0, 0. You just get this constant term, b1. So b naught, the constant term of this rewritten polynomial, has to be the p of 1. b1 has to be p prime of 1. You might at this point suspect, all of these coefficients over here are just the derivatives of p evaluated at 1. So you might think, so b2 is the second derivative of p evaluated at 1. That is not correct. So why is that not correct? So when you take, so let me actually move to the general case. No, I won't move to the general case. Let me write it up here. So now you take p double prime of x, and you differentiate this side the same way we did before. You differentiate the powers of x minus 1 just by the power rule, and the chain rule gives you times a 1, but that doesn't matter. So when you differentiate again, this constant term goes away. The derivative of this is 1. You get a 2b2 plus you get, so we're differentiating again, so you get a 3 times 2. So you get a 3 times 2 times x minus 1 plus a 4 times 3 times x minus 1 squared plus a 5 times 4 times x minus 1 cubed. And you plug in x equals 1, and you get p double prime at 1 equals, all of these terms are 0, so you just get 2b2, which means that b2 itself is p1 double prime over 2. Right? So it's not just p1 double prime of 1. It's p double prime of 1 divided by 2. These didn't have divided by 2. What's going on? I think one more derivative will probably give it away. So let's take the third derivative, p triple prime of x. We get 3 times 2. Yes, I know that's 6. There's a reason why I'm leaving it written out that way. You get 4 times 3 times 2 times x minus 1 plus a 5 times 4 times 3 times x minus 1 squared. And maybe now you see what's really going on. Now you plug in x is 1. This term will be 0. This term will be 0. You get p triple prime at 1 needs to be 3 times 2. I left out what happened to, yes, what happened to all the b's? I left out all the b's when I wrote this, except that first one. Very intelligent. Let's try that again. 3 times 2 times b3, 4 times 3 times b4, right? I was leaving out all of these b's because I just made a big mistake. Plus b5, put in a b5, x minus 1 cubed. That looks a little better. And down here we should have gotten, when we took the derivative, we should have gotten a 3 times 2 times b3 plus a 4 times 3 times 2 times b sub 4. Yes, that was a big mistake. It must be 4 times x minus 1 plus a 5 times 4 times 3 times b5 times x minus 1 squared. So what we get is p1 triple prime at 1 equals 3 times 2 times b3, so that b3 is p triple prime of 1 over 3 times 2. All right. I don't know if you can see what's going on. I would hope so. When we take another derivative, we'll get 4 times 3 times 2 times b4. You'll divide by 4 times 3 times 2. When you go one more derivative, you'll get a 5 times 4 times 3 times 2 times 1, and you'll be dividing by that. You're getting factorials in the denominator. So let me come over here, remind you what factorial is, and write what we're getting. So that I remind you that n factorial, so n is an integer, I think n is an integer greater than or equal to 1 right now, 1 times 2. You multiply all the numbers together, all the natural numbers starting at 1 and going up to n. It's also true that we define, kind of make a special definition, that 0 factorial equals 1. There are a bunch of reasons for this. One of them is the formula that I'm about to write. What we're getting is that if you want p of x to equal this polynomial, then the b's have to be given by the formula b sub k is the kth derivative of p evaluated at a. So I remind you also that when you take derivatives and they're higher than like the second derivative, we don't keep writing primes. We put the number of derivatives in parentheses. So the 0th derivative is just p itself. It's not 1. Right? You just take 0 derivatives, so you just get p of a when k is 0. It's this divided by k factorial. So, for instance, this gives us what we were seeing. We get when b is 0, when k is 0. The 0th derivative of p means just p. So you get p of a divided by 0 factorial. 0 factorial is 1. So you get just p of a. b sub 1 is, this says it would be the first derivative, which we would normally write with a prime, divided by 1 factorial, but that's 1. So we get b1 is p prime of a. In our example, a was 1, so we were getting b1 is p prime of 1. You get b2 is p double prime of a over 2 factorial. b3, and I'll stop writing it soon, p triple prime of a over 3 factorial. 3 factorial is 3 times 2 times 1, it's 6, but it's just good to write 3 factorial. So 3 with an exclamation point after it. And you could do the other ones. I don't have the room to fit them right here, but b4, the 4th derivative of p, evaluated at a, divided by 4 factorial. And you can just keep going. This is much, using this, it's kind of easy to remember. The pattern is nice. And using this, you can rewrite polynomials centered wherever as polynomials centered where you want them at some a value very quickly. So I'm now going to address our real question, which was, let's count, our command. We were commanded, it wasn't a question. Find a degree 3 approximation for this polynomial function when x is close to 1, not 0. Well, it was just a question of rewriting p of x, the function, p of x. But now it's easy for us because all we have to do is calculate the derivatives of this at 1. So I'll calculate the derivatives, and then we'll plug in 1, and we'll know what we need to know. P prime of x, we can calculate derivatives extremely quickly. That's why this is faster than the algebraic approach. P prime of x minus 2 plus 10x plus 45x to the 4 P double prime of x equals 10. That is not a minus sign then. Plus, okay, 160 and 20, 180 x cubed P triple prime of x equals, we just get the derivative of this, so 540 x squared P, the fourth derivative, and now I'll switch to the notation with the parentheses. The fourth derivative of P at x is the derivative of this, 1080 x. And the fifth derivative is 1080. All right, so this is what we get for the derivatives of P. This is not what we need. We need them evaluated, excuse me, we need them evaluated at 1. Right? We're trying to rewrite this as a polynomial centered at 1. We need the derivatives of it evaluated at 1. So what's, and P itself, the 0th derivative. So what's P at 1? All right, it is 4 minus 2, 2 plus 5, 7 plus 9, 16. P of 1 is 16. Okay, right. P prime at 1 is minus 2 plus 10 plus 45. So that is 55 minus 2, 53. P double prime at 1 is 10 plus 180, so it's 190. P triple prime at 1 is 540. The fourth derivative of P at 1 is 1008. 1080. And the fifth derivative of P at 1 is also 1080. What does this mean? This means that our original polynomial, P of x minus 2x plus 5x squared plus 9x to the fifth equals, so it's, all right, b naught plus b1 x minus 1 plus b2 times x minus 1 squared plus b3 times x minus 1 cubed plus b to the fourth times x minus 1 to the 4 plus b sub 5 x minus 1 to the 5, where I'll write it again, b sub k is the kth derivative of p evaluated at 1 divided by k factorial. So we don't just need the derivatives of p that we just calculated. At 1, we need them divided by the appropriate factorial. So b sub 0 is just p1. Right? You just get 0th derivative p evaluated at 1 divided by 0 factorial. We found that that was 6. We found that that was 16. So this is 16. b1 is p prime at 1. So it's the first derivative of p evaluated at 1 divided by 1 factorial, which is 1. P prime of 1 we found was 53. B at 2, or b sub 2. P double prime at 1 divided by 2 factorial. 2 factorial is just 2. what we found was this was 190, but we need to divide by 2, so we get 95. Then b sub 3 is the third derivative of p at 1 divided by 3 factorial. So 3 factorial is 6, so we get 540 over 6, we get 90. All right, so b4 is the fourth derivative of p at 1 divided by 4 factorial. We found that this is 1080 over 4 times 3 times 2. I should say that while we were calculating the derivatives of p, we multiplied times 4 times 3 times 2. If we had left the 4 times 3 times 2 there, we would see how easy it is to do this division, but after we expanded it and now are writing this, it makes it look a lot worse, but it's not. You can divide by 2 and get 540, divide by 3 and you get 180, and divide by a 4 and you get 45. So this is 45. And then b sub 5 is the fifth derivative of p evaluated at 1 divided by 5 factorial. We found that this is 1080 divided by, well, now it's divided by 5 factorial is no, it's not. Let's try this. 4 factorial is 24, so this is 120. And so this is 9. All right, that's what we're getting. As promised, the B5, the coefficient from the highest degree term, has to match this one. So what we're getting is 9, 45, B sub 3 is 90, B sub 2 is 95, B sub 1 is 53, and B naught is 16. So yes, you probably wouldn't guess those coefficients. 16, 53, 95, 90, 45, and 9, although the 9 one is clear. But that's how you rewrite this polynomial in terms of powers of x minus 1. You use that the coefficients are the derivatives of this evaluated at the center divided by the appropriate factorial. Our whole goal was to approximate this by a degree 3 polynomial where the approximation is good for x is near 1. That means we would go out to there. So we would take that part as our approximation. So our final answer to what we were, final solution, what we were told to do, would be that this is approximately equal to this part. So is approximately equal when x is close to 1. Right? Because it's true over here. All right. This has been kind of a warm-up for what we want to do later with functions that aren't polynomials. We want to approximate them by polynomials. And these coefficients that we found, these b's, that are the derivatives of the other function evaluated at the center divided by the appropriate factorial, these will come up for us over and over again. But the reason it comes up, if you understand this section, you'll understand so much of what we do later. And let me reiterate the points of this section. It's when you have a polynomial in powers of x, and x is close to 0, then it's the lower degree terms that are the most important, and you can get a good approximation by discarding higher degree terms. So you take the partial sums, where you only take some of the summation that's defining the polynomial for you, and you get good approximations. If you want to approximate a polynomial well near some other value, so not for x close to 0, but you want to approximate a polynomial well when x is close to 17, then you would want to be given the polynomial as centered at 17. You would like to have powers of x minus 17. And then the same principle holds. The higher powers of x minus 17 don't matter as much when x is close to 17, because then x minus 17 is close to 0, and higher powers of 0, or higher powers of numbers closer to 0 are closer to 0. So yes, if you want to approximate a polynomial well near x equals 17, you want the polynomial given to you as centered at 17, so in powers of x minus 17. Suppose, though, that you're given a polynomial in powers of x, or just given a polynomial function, regardless of how it's written, and you want to write it as a polynomial centered at 1 or 17, then what do you do? And that's the last topic that we were covering. If you're given some polynomial function and you want to write a polynomial function that's equal to it, but centered at x equals a, then to find those coefficients that go in front of the powers of x minus a, you just take derivatives of the polynomial you're given. So you take derivatives of that, evaluate it at the center, so a in general, and divide by the same factorial as the number of derivatives you've taken. And that cool process gives you the coefficients that go in front of the powers of x minus a, so that then you can approximate your original polynomial well. So you have this polynomial function, you want to approximate it well near x equals a, so in this example x equals 1, you just take the first few powers, the first few terms, so one of the partial sums, but after you've recentered the polynomial at a, so in this example at 1, by calculating these new coefficients. All right, in the next section we will talk about approximating other functions other than polynomials well by approximating them well using polynomials.